Hello everyone. Today I'm presenting our work on hybrid CNN-based deepfake image detection with enhanced cross-forgery generalization. This work is a collaboration at Bu Ali Sina University, and I would like to acknowledge my co-authors Hanie Zomorrodi, Atefeh Mosafer, and Professor Hassan Khotanlou. Let me walk you through our approach, which is detecting manipulated facial images. So, what are we trying to achieve? Um, First, providing an efficient method for detecting fake images and distinguishing them from real ones is our primary objective. Reducing errors in identifying different types of fake facial images. Not all forges look the same. And the third one, which is the most one, is improving the generalization ability of the model to detect unknown or new fake images. We want to solve this problem. And the fourth one is extracting more effective and complementary features from facial images. One type of feature isn't enough. We need multiple perspectives. And the last one is providing a model that is robust in against change in forgery methods. Before I explain our solution, I want to be clear about challenges we faced. The first one is the imbalance of fake and real classes. The second is heterogeneity of fake patterns, different manipulation methods. A model that learns only one pattern will fail on others. The third one is dependence on face detection quality. If our face cropping isn't accurate, the entire system will suffer. And the last one is high structural and perceptual similarity between real and fake samples. Let's go to what others did in this area. For example, in 2022, Shihora and his colleagues proposed an interesting method called self-blended image or SBI, which is in the right side of the slide. Uh, Here is the key inside of their approach. Instead of combining different people's face to create forgeries, which is what typical deepfakes do, they manipulate a single facial image to introduce subtle inconsistencies. Things like color mismatches, blending boundaries, and misaligned highlights. The outcome is on the left side of the slide. Think of it like this. If you only practice detecting one type of fake ID, you will miss others. But if you train on many subtle inconsistencies, you become a better general detector for sure. The second work, which has done in 2023, is a research that investigated by Shu I et al. Their method uses a dual stream architecture. It uses two parallel paths working together. Path 1 focuses on semantic content, analyzing the visual appearance of the face to detect anomalies in expressions, identify and detect the identity, consistency, and structural integrity. The second path operates in frequency domain, looking at high frequency artifacts and texture inconsistencies that manipulates the artifacts. You see, when someone manipulates an image, they often leave traces in the frequency spectrum that are invisible to the human eye but detectable by algorithms. Here's what we are going to cover in our final architecture. Okay, you can see our main architecture in a graphical abstract, but let's go through it step by step. Uh, as we know FaceForensics contains videos, not individual images. Each video has a varying number of frames, from 5 frames up to over 1,800 frames per video. We needed to extract a balanced set of facial images from training. For example, for fake videos, we randomly selected 10 frames from each video. For real videos, we selected 60 frame from each video to get a balanced data set. In the second step, we are going to crop and detect the face in the image. For example, we use the hair cascade frontal face detector, specifically the pre-trained model which provided in OpenCV library in Python. It is based on the AdaBoost algorithm. This detector is effective across varying lighting conditions, poses, and the scenes. Here's the process we did. Each frame is converted to grayscale. Then the classifier scans the image and returns bounding boxes around the face. We crop the image to these bounding boxes, and then we resize them to a uniform size. In the next part, and which is the most and core part of methodology, uh, we use two complementary CNN pre-trained CNNs running in parallel, ResNet 1.1 and EfficientNet v2 small. Uh, Forgery artifacts manifest at multiple scales. Some manipulations leave global structural inconsistencies like a misaligned jaw or unusual expression. Others leave local textures, which are anomalies like inconsistent skin pores or blurred boundaries around the eye, for example. After the feature extraction was completely done, we utilized four multi-layer perceptron for the final classification. Uh, as you know, the MLP's job is to learn nonlinear decision boundaries that separate real face from the fake ones in the high dimensional feature space. This design minimizes overfitting while maintaining high classification accuracy. At the end, when it comes to the final loss function, we utilize cross entropy loss by combining with cosine matrix center loss with a control with a term called lambda, which controls the effect of CMCL, and it was set to 0.02. We will go through this what CMCL loss function is. But for the generalization and cross-forgery task, we utilize three modules, and the ICDI stands for interclass data interaction is the first one. This is an advanced data augmentation technique, but it is fundamentally different from traditional augmentation. It focuses on cross-class interaction, blending information between real and fake images. For example, we take an image from one class, for example, a real face, and combine it with information derived from the opposite class, a fake face. This could involve mixing pixel values, blending features, and combining frequency components. The result is a neo hybrid training sample that is neither fully real nor fully fake. The second module is DDFI, stands for Dual Domain Feature Interaction module. The key insight here is that forgery artifacts manifest differently in different representation of the same image. Most deepfake detectors look only at the spatial domain, the image as we see with our eyes. But there is another way to represent image, the frequency domain, obtained uh, by applying a Fourier transform. In the frequency domain, we can see how pixel values change across the image in terms of low, middle, and high frequency. Here is what important manipulation introduces characteristic artifacts in the frequency domain, particularly in high frequency regions, if we are looking for an anomaly. The last thing we have done in our architecture was the label smoothing in the cross entropy laws. It was set to 0.25. It was set to prevent the model overconfidence and enhance the generalization to unseen dataset. Simultaneously, it improves the calibration and uh, generalization. For the evaluation part, we use, as I mentioned, we use FaceForensics the standard benchmark for deepfake detection. It utilized four sub dataset called deepfakes, face-to-face, face swap, and neural textures. We split our data um, to 70, 10, and 20 for training, validation, and testing. As a result, in the table, we can obviously see that compare our method against prior work from the 2021 to 2025. We achieved a 98.26% accuracy and 99.84% AUC at performing all comparable approaches on both metrics. But in the cross-forgery generalization results, we can see that our method generalizes exceptionally well across all scenarios. We get better result uh, in 9 out of 60 states as highlighted in the table. At the end, we can conclude that our method um, outperforms with all comparable state-of-the-art methods. It extract rich local and global features by combining two uh, pre-trained CNN-based model at the same time in parallel. Uh, Also, we introduced three innovation modules, uh, which are ICDI, TTFI, and CMCL for the cross-forgery generalization. And if I want to give you the key message is that our method doesn't just memorize forgery patterns, it learns generalizable features that transfer to new manipulation techniques. This is exactly what real-world deployment requires. For the future work, we are going to test on more diverse and larger scale datasets beyond FF+, and we are going to improve feature interaction mechanism, perhaps at multiple scales, not with involving the attention-based function, and um, maybe involving and integrating novel deep learning models like wheat or swing transformers are a good idea for the next work. And at the end, if you have any question, I would like to answer them. And thanks for your attention and time.